experimented, okay, with to estimate the effects of various actions and decisions. So the thing about simulation is that you are able to use it as a way by which you can test certain ideas you might have, and also come up with various scenarios and try to see what if this were the scenario. So how is this going to affect a certain variable you want to test? So advantages of this method are numerous. First, it's pretty straightforward and flexible. Second, with the recent advances in software, this would make it easier for simulation models to be developed. Third, it can be used to analyze large and complex real-world situations that cannot be solved by conventional quantitative analysis models. So this gives us a chance to be able to handle large and complex data so that we will be able to come up with better decision-making. Fourth, it allows also what-if types of questions. Just as I mentioned earlier, when you have simulation, this can enable us to come up with various scenarios and for us to test each scenario and see what would happen if we were to be confronted with a specific situation. Fifth, these do not interfere with the real-world system. So you can afford to keep doing it over and over again, because you know that this would not redound to an actual cost that will be incurred by the company had you done this method in the real world. So another advantage is that simulation would allow us to study the interactive effect of individual components or variables to determine which ones are important. So in a way, it can be like some kind of a screener of sorts, where you are able to determine which variables to just focus on eventually and which variables to drop. Because there might be some variables that even if there are certain effects, this may not necessarily be very, very significant. And so therefore, you can drop those types of variables and instead concentrate or focus on those variables that really are more relevant in the situation. 7, another advantage is the possibility of time compression. So the time horizon, even if it is important in real life, you can compress the time and get to see what would happen over a broader period of time, for example. Number 8, simulation would allow also the inclusion of real-world complications that most quantitative analysis models cannot permit. So whereas other techniques might have their own limitations, in this case for simulation, it allows for a bigger chance of you to be able to include a certain complex information or realities or incidents that can be used in this technique that cannot be explored had you tapped other techniques. Of course, if it has its advantages, then obviously it also has its disadvantages. And these are some of those. First, good simulation models for complex situations can be very expensive. So, with the extent of data that you handle, among other things, you would need some kind of software that might be pretty expensive to do. And then, of course, because of the time that you expend doing the what-if situations, then this can take a lot of time and therefore the cost can add up. Second, simulation does not generate optimal solutions to problems as do other quantitative analysis techniques like EOQ, LP, or PERD. So it is essentially a trial and error approach that can produce different solutions in repeated runs. So therefore, I repeat, this is not an optimality technique. It's not a technique that would be pretty straightforward when it comes to an actual solution, because every time you repeat it, this might yield different solutions. Third, managers must generate all of the conditions and constraints for solutions they want to examine, because the simulation model does not produce answers by itself. So definitely the use of the software or the use of the model is dependent on the user and the one who's going to handle this technique. So it cannot generate all the necessary conditions or constraints for that matter. It would depend on the one who is handling the simulation itself. Okay, so whatever output you come up with is dependent on the input that was provided by the user. And 4, each simulation model is unique and therefore its solutions and inferences are not usually transferable to other problems. Okay, so every simulation output, okay, and also model is a one-of-a-kind thing. Okay, it will only apply to a specific set of circumstances, and this is not transferable to other situations. Okay. So given that we have both advantages and disadvantages, you'll notice that based on what I just given you, it seems that advantages far outweigh those of the disadvantages. Okay. Now let's proceed and focus on one type of simulation, which we call Monte Carlo simulation. An idea why it's called Monte Carlo? What's so significant about this name? Monte Carlo is what? Casino, okay, it conjures up ideas of gambling, casinos, okay, in Monte Carlo, which is located in Monaco, yes, okay. The Principality of Monaco, okay. So there. Now, Monte Carlo simulation, okay, is a method of simulation that experiments with probabilistic elements of a system by generating random numbers to create values for those elements. So this might be examples of those variables that you might want to simulate. You can simulate, for example, inventory demand on a daily or a weekly basis. That's one. Another application would be in terms of lead time for inventory orders to arrive. Okay. Still another one, the times between machine breakdowns can also be simulated. Also, times between arrivals at a service facility. Same also with service times. And also times to complete project activities. And also number of employees absent from work each day. I'd like to ask the group, is there anybody here who has made use of this technique in his or her work? Or, yeah, was there any opportunity where you had to make use of simulation? Undergrad, your undergrad thesis. What did you have to simulate?
With Dr. Curry's project with the FA.
So you were yeah, okay. Yeah, he's an econometrician. So when you have econometrics, chances are yes, you're going to be heavy into the usage of simulation, where you try to simulate an entire economic system, for example, and try to see what the effect of some economic variable or sets of variables are. Yes. Okay. So what did you end up with? Like what was the issue and what was the main output?
I can't remember the findings, but it has something to do with the simulation of migration to Manila.
Migration to Manila. Okay.
With
Simulation of migration from neighboring provinces or from outside of the country?
from rural areas.
From rural areas, I see.
To urban, depending on the income, GDP, investment, I think.
Those variables were tested, in other words.
Time series analysis.
Also, I see. Okay. Any other one of you who is pretty familiar with the technique, simulation? Or have you done something similar in your work? No? Are you sure that you have not, in your entire life, simulated anything? Oh, come on. Nothing? You don't even get to simulate how it is going to be without 1 peso in your pocket? I mean, I'm sure you played around with maybe the remaining resources that you have and you play out scenarios, for example, and try to see, okay, so at least, okay, by the time I get my next paycheck or whatever, okay, I only have this much amount left, so that's how you are going to survive day by day, okay, by, making do with what you have left. Or maybe some other more creative ways, like maybe I'm just going to visit my friend and ikitain na lang ako. So those things and then other things. Okay? So maybe you might have used it in some practical way, except that maybe not in its entirety, but some elements, more or less, okay, of simulation. So it's not necessarily probably a totally alien technique to you. Okay? And then now you say, so that's the one that I've been doing all this while. Let's try to see how you can do it the more scientific way. Okay? So, 5 steps in Monte Carlo simulation. Okay? First, let's just go through this one by one. You set up first a probability distribution for important variables. Okay? You have to decide first which variable you are going to focus on, or the variables that you're going to focus on. So when you set up a probability distribution, okay, here you try to see the proportion of that occurrence, the frequency, okay, based on the total possible number of occurrences. And so once you're able to do that, then you can proceed to the next step, which is building a cumulative probability distribution for each variable mentioned in step 1. So cumulative probability distribution simply means that as you progress through, okay, the probability distribution, then you get to just simply add on until you get to total probability of 1. Okay. Then third, establish an interval of random numbers for each variable. And fourth, generate those random numbers. Lastly, actually simulating a series of trials. Now, the accuracy of the simulation depends on the frequency of trials that are conducted. The more you repeat, and the more that you repeat the simulation, then the closer you get to the theoretical expected value. That's right. So let's just say that we have this example. Let's say Harry's auto tire example. Sells all types of tires, but the popular radial tire accounts for a large portion of Harry's overall sales. Now, if we recognize that inventory costs can be quite significant with this product, Harry wishes to determine a policy for managing this inventory. And so, therefore, in order for him to see how the demand would look like, okay, over a period of time, he wishes to simulate the daily demand for a number of days. So, first step, as we said, we establish the probability distributions. Okay. Now, one common way to do this is to probably look through your historical data and try to see essentially try to recall or try to see, okay, what the demand was over a period of time. Okay. But historical data need not necessarily be the only way by which you can do this. Okay. Sometimes you might make use of something as, like maybe based on other patterns that you get to see, like whether it's normal, okay, Poisson, or exponential patterns for that matter. So it need not necessarily just be based simply on just historical data. Okay. Now let's just say that the daily demand for radial tires at Harry's Auto Tire over the past 200 days, let's say, is represented by this specific table. Okay. So let's just say that the demand for tires, daily demand, remember it's demand for tires on a daily basis, either be 0, 1, 2, 3, 4, and 5. Now the same instance, okay, we look at the frequency in terms of days. Okay. So, how many days did demand reflect at 0, reflect at 1, 2, 3, 4, and 5. So let's just say that based on historical data, the frequency was as follows. If you have a total, the number of days of 200, let's say 10 days reflected 0, 20 days, okay, reflected demand for just one tire, 40 days, okay, reflected demand for 2 tires, 60 days reflected for 3, 40 for 4, and lastly 30 for 5 tires. Okay, so establishing probability distribution, we try to see, okay, the probability of occurrence, okay, and we can get this essentially by just simply dividing the frequency by the total number of days. Okay, so in this case, probability of occurrence will be how much? 5%, 0.5. Next would be what? 10. Okay. Next, 20, 30, 20 again, and 15. So total, if we added everything up, is probability of 1. So this is the probability distribution table that I was talking about. Now, once you're able to do that, then the next step here would be to compute for the cumulative probability. So therefore, if we start with 0.05, what's the cumulative probability of the next? 0.15, then 0.35, and 65, 85, 1. So we have already satisfied the 2 steps, okay, in our Monte Carlo simulation. So third step, set the random number intervals. So once you already have established the cumulative probability distribution, you need to assign a set of numbers to represent each possible value or outcome. So these are what we call random number intervals. For example, if there's a 5% chance that the demand for a product is 0 units per day, then we want 5% of the random numbers available to correspond to a demand of 0 units. Let's just say we have a total of 100 2-digit numbers, okay, used in the simulation. You can think of them as numbered chips in a bowl. So you have 100, okay, chances there. In that case, you could assign a demand of 0 units to the first 5 random numbers, 01, 02, 03, 04, and 05. So therefore, every time you get to the actual simulation and you pick one number from that bowl, and you see that it would fall within that range, 01, 02, 03, 04, 05, then you know that this would correspond to a demand of 0 tires. Get it? What if, let's say, but the thing is, we need to do first the intervals, okay? So let's just say that we have the following interval of random numbers. Of random numbers. So let's just say we already assigned that 01, let's say 205 will correspond to 0 demand. Okay. Now in the next, okay, it would seem that we have, okay, in order for us to correspond, let's say, to a demand for 1, okay, let's just say that we assign 06 to 15. Okay. So how did that happen? How many numbers do we have here? 10. If this is 5% and we have 5 numbers, then we have 10% and we have 10 numbers, then what is next? Okay, let's say if we assign 16 to 35 as the next range, that means any number, if you pick, let's just say again from the bowl, and you got 34, then this would correspond to the demand of 2. You get that? Here, 2. Okay. So the next, okay, so you have your 36 to 66 to 85, and 86 to 100. 0, 0. Tama ba? 6, 6, 7, 8, 9, 19. Tama ba? 15? Okay. Okay? So once you're able to do this, okay, then you go through that actual simulation. Okay? As I mentioned, you pick, okay, and try to see how this would affect your your desire to find out what demand for tires to come up with. So when you do this, you try to see if based on the data that we have, we can come up with the expected daily demand. Okay, and this, okay, we can get to compute as follows. Wherein you have the summation, okay, of the probability of IF tires, okay, times the demand, okay, of I tires. Okay. So this means, for example, based on this, you have 0.05 times 0 plus what? 0.10 times 1 plus 0.20 times 2 plus 0.30 times 3 plus 0.20, that's the probability, times 4 plus 0.15 times 5. Try to see if your final result will end with 2.95 tires. Okay. Let's just say we started, okay, so we do that, no? And we check. So this is where we do the actual simulation already. Again, remember the 100 chips that you had more or less in the bowl. You can also use a table of random numbers. Okay? In other words, you try to give an equal chance of each chip, for example, or each number to be picked. You can even generate it from the computer. Okay? So let's just say that we do the actual simulation. And let's say we ended up with the following, where in the simulated daily demand, okay, let's just say this is the result of our actual experiment. The first run, for example, ended up with, let's say the number that we got here was 52 for the first day. Okay, let's put this as day 1. Anyway, let's equalize this table. Based on this, say this is the result of our simulation. 8, 9, and 10. Day 1, random number, let's say that we drew were the following. You have 52, 37, let's say 82, 69, 98, 96, 33, 50, 88, and 90. Then you have here the simulated daily demand. So you have here, let's say, 3. Okay, why 3? 52 is 3, right? 37 is 3. 82 is 4. 69 is 4. 98 is 5. 96 is 5. 33 is 2. 50 is 3. 88 is 5. 90 is 5. If we were going to add all of this, we have 39. And so therefore, divided by 10, our average daily demand would seem to be 3.9 tires. Okay. You notice that this one is still a bit far from this one. But if you keep repeating, let's say you did this 1,000 times, it is expected that this is going to slowly approach this one. Okay? So that's the intention there. The accuracy is affected by the number of trials. Okay? That's why when, let's say, you are going to conduct something similar for business research, layo pa, Malapit na. Okay, something like that, okay? Then, the number of repetitions is going to have a bearing on your final result. If we did this again, the chance that you can pick out more or less the same will be a lot different, okay? So this might be different, and so we will see whether eventually this one should approach that simulated demand figure of 2.95. So you're running at something about 3. This is closer to 4, okay? So you have the difference between about 3 and 4. Questions? Sounds very simple, no? Sounds very, yes.
Hindi po natin i-repeat yung random number.
Usually, you would. You try to see, kasi magbabago yan eh. Di ba?
Ang simulate lang yung number lang.
You're going against also set up probability if you're returning. Let's say you allow the user to take it again. Let's say you pick.
Yes, this one. Okay.
Pero,
ulitin mo yung trial, tatanggalin mo muna siya. I mean, each of this, diba? Tatanggalin mo muna din siya. Ganon. Tapos, when you do again the trial again, it's as if you're starting from 0 again. So kumbaga, again, you're giving again the equal probability again that you will pick essentially whatever. Basta kompleto yung 100 na yun ulit when you repeat the trial. So, essentially, pwede siya magbago-bago. Okay, essentially. Each trial is like a certain different.
Ibig sabihin, isang parang
Kasi kung
babaguhin mo lahat.
this number, so whatever, tapos yung natitira doon kung kukunin na hindi na siya random in that case. Kasi hindi mo simulated dati, so you don't give an equal chance for all those chips to be picked again. Diba? Yes?
By some stroke of luck, nakuha ang pattern. Let's say 2.9501, hindi mo nakuha. Nire-run ka pa.
Of course, mag-rank ka pa rin. Kasi we want to see whether that is going to be maintained then. Essentially, diba? So yun yung, in other words, like given again the same conditions or whatever, then if we were, if everything else again were like all equal or whatever, would you still have the same result, essentially? Of course, you're going to get different, that's sure, no? But then, once you're able to see whether the numbers would veer towards a certain direction, or they would really be scattered, whatever, then that means that you might have to still do more simulated trials. That would just give you the idea that essentially you still have to keep doing those trials.
Meron bang number of times na yung in-run yung trial or dire-diretso lang?
Remember, this is very expensive. So, yeah, it's up to you. Okay. There was one student, the master level, okay, wherein I was like a member of his committee, no? And he was doing some kind of simulation. Okay, he was MS Statistics. He just graduated actually. And so I was asking him, how many times did you run your simulations? And he said, actually, I was only able to run it, what did he say? He could not hit the 1,000 because he said, no, it's going to be very expensive for the university because the funding was going to come from the university. So I think he stuck, with, I'm not sure if it's 500 trials or something. And so, yeah. So of course, then, the limitation there is you will have to claim that the results here are just based on the limited number of runs. If he doubled that, more or less, it's possible that it could have changed again what he might have found out in the system. Other questions? Yes.
Paano ka lalapit doon sa 2.9? I-average mo yung result mo gala?
Yes. I-average mo siya. Okay.
Pwede po bang...
You want to see what your possible rate might be? Yes, who's asking a question? I'm sorry. JD, yes, JD.
May possibility po na mas bumaba sa 2.95.
Yeah, possible. Yeah, I don't know. It's possible. Oo, kung mas pa yung mga numbers na namin nagka-cluster lang dun lang sa range na pinili mo. But remember whenever you're going to do the simulated trials, kung ano yung range na in-agree mo, that's it. Nakaset. Oo, yun yung ano mo, yun yung naset mo at the time. Questions? Okay, so if not, then let's continue with the discussion. That was just the example for Monte Carlo. Monte Carlo is just one of those other techniques that are used. Okay, you have two other types of simulation models. One would be operational gaming. Refers to simulation involving two or more competing players, like military games, business games. What games do you play on the computer? Operational gaming games. You try to simulate, okay? Try to see if, let's say, you
Ayaw
can
mag-load ng Magic ko.
end up with a lot of money for
2040.
that matter. That's the
Magic
objective of the game.
Ayaw eh.
Bukas tingnan ko.
Or if you can capture other territories, like in some games, yes. Sa? Game, oo. Game. Medyo. Probabilistic kasi, di ba? Oo. It's probabilistic. So in that sense, yes, it's related. Another type of simulation model would be what we call systems simulation, just what I was mentioning a while ago about econometric models. Okay, so systems simulation is similar to this is gaming in that it allows users to test various managerial policies and decisions to evaluate their effect on the operating environment. And this variation of simulation models, okay, the dynamics of large systems like corporate operations, the national economy, okay, a hospital or a city government system. I don't know if you encountered the terrible traffic in Calamba when they tried to shut off that route leading to the city hall. You had a shortcut? Did you encounter massive traffic there? Yeah, okay. So at the back of my mind when I heard about that, because my husband was complaining, he would usually leave at 4:30 in the morning on a Monday. He said, imagine what time I got to, in other words, he was there for practically an hour and a half to 2 hours just in that intersection, okay, in Calamba. Because of that, he said what bird-brained person felt about yeah, trying to cut off like one of those possible arteries to decongest and the capacity cannot be absorbed by that simple route. Probably they did some kind of simulation way beforehand and they could see whether it would work or not, okay? So that might be one possible use also for this technique. So, anyway, the thing with simulation is that there are two important V words, in other words, starts with the letter V, that have to be recognized and therefore applied whenever you use these models. First is verification. Okay? There has to be verification and validation. And how do we distinguish between these two? Verification answers the question, did we build the model right? Okay. You try to determine if the computer model is internally consistent with the conceptual model. Did we build the model right? Verification. Whereas validation answers the question, did we build the right model? Okay. Comparing the model to the real system that it actually represents to make sure that it is accurate. So did we build the model right or did we build the right model? So one is verification, the other one is validation. Okay. And that ends the lectures for Monte. Okay. And so, good news is there's no more problem set or exercise. Sorry about